Quantum computing is currently one of the most exciting emerging technologies, and it's almost certainly a topic that will continue to make headlines in the coming years. But there are now so many companies working on quantum computing that it's become really confusing. Who is working on what? What are the benefits and disadvantages of each technology? And who are the newcomers to watch out for? That's what we will talk about today. Quantum computers use units that are called quantum bits or qubits for short. In contrast to normal bits, which can take on two values like 0 and 1, a qubit can take on an arbitrary combination of two values. The magic of quantum computing happens when you entangle qubits. Entanglement is a type of correlation, so it ties qubits together, but it's a correlation that has no equivalent in the non-quantum world. There are a huge number of ways qubits can be entangled, and that creates a computational advantage if you want to solve certain mathematical problems. Quantum computers can help, for example, to solve the Schrödinger equation for complicated molecules. One could use that to find out what properties a material has without having to synthetically produce it. Quantum computers can also solve certain logistic problems and optimize financial systems. So there is a real potential for application. But quantum computing does not help for all types of calculations. Quantum computers are special purpose machines. They also don't operate all by themselves, but the quantum parts have to be controlled and read out by a conventional computer. You could say that quantum computers are for problem solving what wormholes are for space travel. They might not bring you everywhere you want to go, but if they can bring you somewhere, you'll get there really fast. What makes quantum computing special is also what makes it challenging. To use quantum computers, you have to maintain the entanglement between the qubits long enough to actually do the calculation. And quantum effects are really sensitive, even to smallest disturbances. To be reliable, quantum computers therefore need to operate with several copies of the information together with an error correction protocol. And to do this error correction, you need more qubits. Estimates say that the number of qubits we need to reach for a quantum computer to do reliable and useful calculations that a conventional computer can't do is about 1 million. The exact number depends on the type of problem you're trying to solve, the algorithm and the quality of the qubits and so on, but as a rule of thumb, 1 million is a good benchmark to keep in mind. Below that, quantum computers are mainly of academic interest. Having said that, let's now look at what different types of qubits there are and how far we are on the way to that million. Superconducting qubits. Superconducting qubits are by far the most widely used and most advanced type of qubits. They are basically small currents on a chip. The two states of the qubit can be physically realized either by the distribution of the charge or by the flux of the current. The big advantage of superconducting qubits is that they can be produced by the same techniques that the electronics industry has used for the past 5 decades. These qubits are basically microchips, except here it comes, they have to be cooled to extremely low temperatures, about 10 to 20 millikelvin. One needs these low temperatures to make the circuits superconducting, otherwise you can't keep them in these neat 2-qubit states. Despite the low temperature, quantum effects in superconducting qubits disappear extremely quickly. This disappearance of quantum effects is measured in the decoherence time, which for the superconducting qubits is currently a few tenths of microseconds. Superconducting qubits are the technology which is used by Google and IBM and also by a number of smaller companies. In 2019, Google was first to demonstrate quantum supremacy, which means they performed a task that a conventional computer could not have done in a reasonable amount of time. The processor they used for this had 53 qubits. I made a video about this topic specifically, so check this out for more. Google's supremacy claim was later debated by IBM. IBM argued that actually the calculation could have been performed within reasonable time on a conventional supercomputer, so Google's claim was somewhat premature. Maybe it was. Or maybe IBM was just annoyed that they weren't first. IBM's quantum computers also use superconducting qubits. Their biggest one currently has 65 qubits, and they recently put out a roadmap that projects 1,000 qubits by 2023. IBM's smaller quantum computers, the ones with 5 and 16 qubits, are free to access in the cloud. The biggest problem for superconducting qubits is the cooling. Beyond a few thousand or so, it'll become difficult to put all qubits into one cooling system, so that's where it'll become challenging. Photonic quantum computing. In photonic quantum computing, the qubits are properties related to photons. That may be the presence of a photon itself or the uncertainty in a particular state of the photon. This approach is pursued, for example, by the company Xanadu in Toronto. It is also the approach that was used a few months ago by a group of Chinese researchers, which demonstrated quantum supremacy for photonic quantum computing. The biggest advantage of using photons is that they can be operated at room temperature, and the quantum effects last much longer than for superconducting qubits, typically some milliseconds, but it can go up to some hours in ideal cases. This makes photonic quantum computers much cheaper and easier to handle. The big disadvantage is that the systems become really large really quickly because of the laser guides and optical components. For example, the photonic system of the Chinese group covers a whole tabletop, whereas superconducting circuits are just tiny chips. The company PsiQuantum, however, claims they have solved the problem, and they claim to have found an approach to photonic quantum computing that can be scaled up to 1 million qubits. Exactly how they want to do that, no one knows, but that's definitely a development to have an eye on. Ion traps. In ion traps, the qubits are atoms that are missing some electrons and therefore have a net negative charge. You can then trap these ions in electromagnetic fields and use lasers to move them around and entangle them. Such ion traps are comparable in size to the qubit chips. They also need to be cooled, but not quite as much, only to temperatures of a few Kelvin. The biggest player in trapped ion quantum computing is Honeywell, but the startup IonQ uses the same approach. The advantages of trapped ion computing are longer coherence times than superconducting qubits, up to a few minutes, and the other advantage is that trapped ions can interact with more neighbors than superconducting qubits. But ion traps also have disadvantages. Notably, they are slower to react than superconducting qubits, and it's more difficult to put many traps onto a single chip. However, they've kept up with superconducting qubits well. Honeywell claims to have the best quantum computer in the world by quantum volume. What the heck is quantum volume? It's a metric originally introduced by IBM that combines many different factors like errors, crosstalk, and connectivity. Honeywell reports a quantum volume of 64, and according to their website, they too are moving to the cloud next year. IonQ's latest model contains 32 trapped ions sitting in a chain. They also have a roadmap, according to which they expect quantum supremacy by 2025, and they expect to be able to solve interesting problems by 2028. Before I tell you about D-Wave, I briefly want to thank our Tier 4 supporters on Patreon. Your donations are of great help to keep this channel going. And you too can help us. Go check out our Patreon page, the link is in the info below. Now, what about D-Wave? D-Wave is so far the only company that sells commercially available quantum computers, and they also use superconducting qubits. Their 2020 model has a stunning 5,600 qubits. However, the D-Wave computers can't be compared to the approaches pursued by Google and IBM, because D-Wave uses a completely different computation strategy. D-Wave computers can be used for solving certain optimization problems that are defined by the design of the machine. whereas the technology developed by Google and IBM is good to create a programmable computer that can be applied to all kinds of different problems. Both are interesting, but it's comparing apples and oranges. Topological quantum computing. Topological quantum computing is the wild card. There isn't currently any workable machine that uses this technique, but the idea is great. In topological quantum computers, information would be stored in conserved properties of quasi-particles that are collective motions of particles. The great thing about this is that this information would be very robust to decoherence. According to Microsoft, the upside is enormous and there's practically no downside. In 2018, the director of quantum computing business development told the BBC Microsoft would have a commercially relevant quantum computer within 5 years. However, Microsoft had a big setback in February when they had to retract a paper that demonstrated the existence of quasi-particles they hoped to use. So much about no downside. The far field. These were the biggest players, but there are two newcomers that are worth having an eye on. The first is semiconducting qubits. They are very similar to the superconducting qubits, but here the qubits are either the spin or charge of single electrons. The advantage is that the temperature doesn't need to be quite as low. Instead of 10 millikelvin, one only has to reach a few Kelvin. This approach is presently pursued by researchers at TU Delft in the Netherlands, supported by Intel. The second are nitrogen vacancy systems, where the qubits are places in the structure of a carbon crystal where a carbon atom is replaced with nitrogen. The great advantage of those is that they're both small and can be operated at room temperatures. This approach is pursued by the Hansen Lab at QTech, some people at MIT, and a startup in Australia called Quantum Brilliance. So far, there hasn't been any demonstration of quantum computation for these two approaches, but they could become very promising. So that's the status of quantum computing in early 2021, and I hope this video will help you to make sense of the next quantum computing headlines, which are certain to come. This video was sponsored by Brilliant, which is a website and app that offers interactive courses on a large variety of topics in science and mathematics. Brilliant is a great starting point if you want to know more about quantum mechanics. They have you covered on the math behind quantum mechanics, such as linear algebra and differential equations, and they have courses on the properties and behavior of quantum objects, and even on quantum computing in particular. To support this channel and learn more about Brilliant, go to brilliant.org/Sabine and sign up for free. The first 200 subscribers using this link will get 20% off the annual premium subscription. I want to thank Tanuj Kumar for helping with this video and all of you for watching. See you next week.